Let's do a brief introduction of LLMs. So what is LLM? So LLM is an AI system that's trained on vast amounts of text data and that can interact with human by generating human languages. So LLMs are different because they learn patterns, contexts, and relationships between words through a massive amount of data. And some popular examples of LLMs are GPT-4 by OpenAI company, BERT by Google company, T5 also by Google company, and Llama by Meta company. And LLMs have definitely changed the ways of human daily lives, and it has multiple applications in real life. So some example applications are chatbots, like you can talk to a ChatGPT and it can do translation, grammar correction, text generation, essay writing, text summarization for you. And it can also do NLP-related tasks such as entity recognition, sentiment analysis. And also, if you give ChatGPT a table, Excel table of data, it can also conduct data analysis on the data. And also, LLMs have been used for generation of computer code. So it can write code for softwares. And say if we want to draw a visualization for some data, you can just ask ChatGPT to generate the Python codes for you, and they would give you pretty decent codes, and you can just run to generate the visualization. And ChatGPT has also been used to applied to automation and also workflow building, and it's also very good at generating CSS and designing websites. And here are a few key components of LLMs. So we talk about LLMs all the times, but these are the components that's gonna make LLM happen. So first, the most important part is the data. So LLM's performance highly rely on the data they're trained on. So right now, for those advanced LLMs like GPT-4, they are pretty much trained on all the data we can find on the internet. So data is like the most important component of building LLMs. And we also have different architectures for LLMs, but for most recent LLMs are built on the decoder-only architectures. And the basic unit of LLMs is the transformers, which is also a neural network. And researchers have been exploring different architectures, but recently just found the decoder-only architecture is the most fit for LLMs. And also, when we have the data, when we have the architecture of the models, we need to train the models, and there are a lot of techniques and algorithms involved in the training process of the LLMs. So typically, there's a pre-training phase, there's a fine-tuning phase, there's a instruction tuning phase, and the alignment phase. And through all these techniques, we can make sure that LLMs can understand humans' instructions and also follow human instructions. And the next important component of LLMs is inference. So basically, it's where we are using LLMs. So after the companies train the models, we can take the models and directly use the models in our real world scenarios. And inference is just a process. You just give a prompt to LLMs and it generates the responses accordingly. And those are most of the components that the builder of LLMs are more interested in. And for users, we mostly only care about what LLMs we can use. And one important component of that is to select LLMs is the model parameter size. So LLMs can vary from 1 billion parameters to like hundreds of billions of parameters. Then we need to think about what we're gonna need and how much LLMs can we hold in our local environment. So the parameters is the which is the total number of variables the model holds, is the key criteria when we actually gonna select an LLM to use. And recently, the research has also focused on multimodal LLMs. So instead of only taking text data and generating text, the recent LLMs have also the capability of taking in multimodal data and give multimodal outputs. So the key abilities of the multimodal LLMs is they can understand multi formats of data, such as images, Excel files, videos, audios, and also definitely text. So by integrating all different formats of modalities of data, the models can fuse the information together and understand the context between different formats and then generate reasonable responses. Multimodal LLMs can also reason through the multimodal information. So they are not only taking in the data, but they can actually reason about the data. So for example, if you give a mathematical problem in an image, then the model can read the data, and it can actually reason about the problem and then solve the problem to give you a solution. So I'm teaching the machine learning class this semester, and I tried the ChatGPT for all of my assignments. Actually, ChatGPT is so good; they can almost solve all the problems in my assignments. So that's why I changed to the handwritten midterms and quizzes right now. So also, multimodal LLMs can also learn from multimodal data. So they are not only taking in the data, but they are also evolving with the new data. So as I mentioned earlier, LLMs pretty much has used all of the text data available on the internet. So right now they are starting to take in videos and images and other formats of data to evolve the model itself. And here are a few terminologies that you're gonna hear a lot throughout the talk, like if you read some articles about LLMs. So the terminologies include like foundation models, which is just another name for like a nickname for the large model that can do anything. And the pre-training is the first phase of training for LLMs that take in the huge amount of data and training the data without any supervision. And the tokenization is the process where we give the text to a model and the model change the text into some numerical vectors. So the models can't understand text or images. It can only stand the numerical vectors and those elements. So we need to have a way to transfer all the data formats into the numerical vectors. And that's the process of tokenization. And the numerical vectors we get after the tokenization is actually called embeddings. And fine-tuning is the term that we take a pre-trained LLM and fine-tune on some specific domain and data for better performance in a specific domain. And alignment is the process where we train the models so the model can understand human instructions and can follow the instructions of human beings. And the RAG, retrieval augmented generation, is a process where the model can first retrieve some information from a database and then use the information to assist the generation process. For example, if I ask a question, then probably the model can search the information on the internet, and it can gather some relevant passages or web pages, and it can use the information it found through those web pages to answer the question. So that is the whole process of the retrieval augmented generation. And also perplexity is a way to measure how good language model is. So like usually a model with lower perplexity is better in terms of the generation quality. So why do we actually need LLMs? What are they different from other techniques. So the strength of LLMs in terms of they can understand natural languages. So it's easier for user to interact with ChatGPT. They have the versatility and they also have the knowledge access. So they know pretty much of everything on the internet. So they're also a good way to gather knowledge from the internet. And they also have the scalability and they're continuous improving. So we have seen great progress in the last 5 years. We have from GPT-1 to GPT-4 to GPT 4.5 last week. So we can see the models are evolving and their capabilities are increasing in a good speed. So we could expect we have even more powerful, we definitely will have more powerful LLMs or AI assistants in next 5 or 10 years. And also the LLMs is a good way to provide the accessibility. So it doesn't have too much barrier for users to engage. So language models has been there for 20, 30 years, but nobody cares about language models. But only with the LLMs, it lowers the barrier to enter the field, and everybody right now can use ChatGPT. So I think that's the magic of the LLMs. But on the other hand, there are also a lot of threats for LLMs, such as we pretty much don't understand why LLMs will make some decisions or generate some results. So we don't have any explain or interpretability about the results of LLMs. Also, there's also the privacy related issue about whether my data will be leaked to ChatGPT, or whether there are any security or could LLMs be hacked. And also when we use LLMs to do something bad, such as generating some really convincing personalized phishing emails, how can we stop those? Or like if the students just use ChatGPT to do their assignments, how as a faculty I can detect the AI generated content and make sure they do the assignments on their own. So there are a lot of threats around LLMs at the same time. Another issue about LLMs is the ethical concerns. So say if I generate an image or a painting with LLMs or some diffusion models, then who has the copyright of the generated paintings? Does the company who built the AI model have the copyright? Or does the source of data has the copyright? Or as a user, I have the copyright? So there's a lot of debates regarding that, and there's no regulations right now. And also, there could also be some bias or discriminative outputs from LLMs, and also there could be fake information generated by LLMs. Then, if if the LLMs give you the fake instructions, then you follow instructions. Who's gonna take the responsibility of that? Will the OpenAI company take the responsibility, or will the user take the responsibility? That's there's also a lot of ethical issues regarding that. And definitely, researchers have been working on addressing those issues, such as we try to migrate bias of LMs, we try to protect the data privacy, we try to increase the incident management, but there's still a long way to go. And yeah, as I said, the data ownership is also another question. So LM is trained on all the data on the internet. And who holds the ownership of the data? Is the company actually allowed to use all the data? So that's another problem. And also, if there are some harmful information on the internet, how can we make sure the LMs do not learn from those harmful informations? And also the related copyright issues. So these are the remaining questions of LLMs. And also another possible issue of LLM is the environmental issues. So we all know the LLMs takes thousands of GPUs to train, like tens of thousands of hours to get model training. But with electricity and the carbon emissions, does it actually worth it? Like right now, each company is building their own LLMs. Does it necessary to have so many LLMs? So there are also a lot of environmental related issues right now. And also for LLMs, there's also all the models could be also categorized into open source LLMs versus the closed LLMs. So open source LLMs are those models that we have access to the weights of the models. So the models are open source. Everybody can use it, can download it, can deploy it, or can continue train the models. And examples of those models are Lamar and some open source LLMs on Huggingface. And another group of LLMs are the closed models, which are not accessible, and we don't actually know their weights. We can only access the models through the chatbots in browser or using API. So we can only talk to the model, get the responses, but we can't have access to the model itself. Examples of those are the GPT series from OpenAI and also the cloud from Anthropic. So next, I'll talk about some ways we can interact with LLMs. So I think most of the audience should have access to LLM with the or like ChatGPT with the website browser. So that's definitely one of the most popular way to use LLMs, but there are definitely other ways. So I'll talk about that. So so the use of LLMs also depends on whether the model is closed or open source. So we start with closed LLMs. So for the closed LLMs like ChatGPT, we can definitely interact with the web page chatbot. So we can just go to the chatbot.com, chatgpt.com, and we can interact with the LLMs. But that's pretty good. But what if we have 1,000 documents and we want to process all the documents with the LLMs? We definitely can't directly talk to the chatbot 1,000 times. So the other way to access those closed models is via the API. So API is the process where you can write all your prompts into a format of the function calls, and the program will pass the function calls to the OpenAI company, and the company will send the responses back, and you can take the responses and organize them in a structured way instead of just the plain responses. So here is a typical format of the API call for ChatGPT. So basically, for the ChatGPT, you need to have the name of the agent. So some different models of OpenAI have different names. You can just check their website, and you can check the different specific requirements for the API calls, and you can specify the details parameters, and then you can encode your information as a function call. So basically, you will have the query, and you will get a response, and you can also have some references, and the LLMs will just send those to you. And the good way of the API call is batchable, so you can repeat the same process for multiple tasks for like unlimited times. So if you have 1,000 documents and you want to ChatGPT to summarize each of the document for you, then you can directly use the API call, and you will get the 1,000 summaries directly from OpenAI instead of talking to ChatGPT in the web page 1,000 times. And the other group of LLMs is the open source models, and for those models, we have more options to use them. So the first option is the local deployment. So we can actually download the models and install the model on our local environment or on a server we have. Then you will have your own models, it's gonna only work for you, and you can actually personalize the model by training the models, or like adding your personalized features to the models, so the model can be a personal assistant for you. So I'm gonna show briefly an example of how to deploy the models. So most of the models are held by on the Huggingface platform. So if you go to the Huggingface platform, they have thousands of open source LLMs. You can easily find one that fits you. And if you go to the model page, you can simply click use the models. And if you like all the models are stored in the transformers libraries, and you can simply use these 10 lines of code, and then you can simply download the models automatically and deploy the model on your local computers. So this is very convenient, and it also gives you a protection of your data. So if you deploy the model on your local computers, no one gonna have access to your own data. So you don't need to worry about data leakage. So that's a very good way to use the open LLMs. But for ChatGPT, those closed models we can't deploy because we don't have access to their models. So here is just the code that I showed earlier. So you can simply download and deploy the models on your local computer with this 10 lines of code.
Is that easy to deploy on a server as well?
Yeah, it's the same. Just like the server has a larger GPU memory, so you can even like deploy a larger models. Yeah. So the most of the limitations of deploying LLMs is the GPU memory. So since all the computations of LLMs are on GPUs, then if your laptop don't have a large GPU, then you can only probably download the 1 billion parameter models. Then on the server, you can definitely download the much powerful and larger models. Yeah. And I think that's a really good question, because what if you don't have a good like a laptop with large GPU memories, or what if you don't have a server with good GPUs? Then another way you can access those open models is by using the Huggingface APIs. So Huggingface actually they hold a huge servers, so they also deploy all the models on their own servers, and you can access all the open models Huggingface by using their Huggingface API interface. And the good thing of Huggingface API is like it's very simple. It's basically similar to OpenAI API, so I just follow the format. And another benefit is it holds like thousands of open LLMs, so you can access different models. And another benefit is right now it's still very cheap, so you have 20,000 API calls to the Hugging Face APIs per month for only $9 per month. So I'm not doing any advertisement, but I like for my lab we have been using this, and we found it's pretty easy to use and also pretty cheap. So I'm gonna show an example of here. So let me try another model. So we want to try the Llama model from the Meta company. So if you click the deploy, and you can directly see there are the inference providers and also Hugging Face inference endpoints. And if you click here, you're gonna see how you can deploy those on their Hugging Face servers. Or if you click on the inference providers, you can simply use access the model with the API here. And you can see here is the each account will has an API key, and with the key you can directly send a message. Like you can just like your role as a user, and you can just type your questions, and we do the text completion, and the Hugging Face API will just send the response back to you. So in that way, you can directly use LLMs without need to actually have a fancy GPU in your server. And if you and there are thousands of GPU models there, so you can right now this one using the Llama model, but you can simply switch to other models if you want to use. Here is just the code I showed, where you can directly do the inference on Huggingface. And another option is just to use the cloud servers provided by such as Amazon, SageMaker, or other companies. You can also deploy the models on those cloud servers, but definitely you need to run the server first, and that's gonna be definitely more expensive than using APIs. Also, as I mentioned, there are thousands of LLMs right now, and probably you wonder which model should you choose. So there's also other So researchers has also built this leaderboard, so which we allow everybody to submit their own LLMs, and we have a few benchmarks that we can test the performance of different LLMs. So you can see, but most of the other LLMs are just like the variants of the Llama model, or like the base model from the big companies. They just take the checkpoint and continue to train the models. But you can see here is a leaderboard. You can simply choose good models from the leaderboard to see if they are gonna be good for your applications. So they hold actually the benchmarks on different aspects, such as request answering, instruction following, and other capabilities. You can just check their performances. And there's also another leaderboard. This is not tested on benchmarks, but this is voted by the community. So everyone using LMs can vote in this leaderboard, and we also have this vote to specify which LMs is specific. So if you have a question of which LMs to use, then you can simply refer to this leaderboard. The links is also on the bottom. Yeah, so that's pretty much of the first part about LMs, and the next part I'll talk about summarization. So we're living in the era of big data, and the data has surrounds us everywhere around us in different formats. And ever since we have internet, we have really huge amounts of raw data. So for example, for 1 minute on the internet in 2020, we have 200,000 participants in meetings. We have 300 new users in X platforms. So there's so much data on the internet that we, as a human beings, we can process. So human average process information, for example, in 2022. So we read almost 1,600 articles yearly, but we actually only read fully 300 of them. We have checked 10,000 pages, and we do more than 3,000 searches yearly. And usually we have a lot of tabs open in our browser all the times. At least that's for me. So that's gonna result in the problem of information overload, where an individual is exposed to more information than it can effectively process or manage. And that could lead to many harms, such as poor data retention, low mental energy, and decreased productivity. For example, if I give you this slides, then probably nobody gonna read it. Right. So, but the good thing is we have the summarization, also the AI powered summarization. So we actually don't need to browse all the information, but we can only check the salient information. And summarization is the tool where we can distill text into smaller and more digestible pieces. So the definition of summarization is to produce an averaged version of a text while retaining the key relevant information. And the summarization approaches can be categorized in different groups based on the input format and output format. So from the input set, we can format summarization as a single document summarization task, multi-document summarization task, and also query-focused summarization task. And in terms of the output, we can generate extractive summary, we can generate abstractive summaries, and we can also generate hybrid summaries. So single document summarization is the simplest case. So we read the document, we read an article, we just need to write a summary about the article. So that's the simplest case. Another case is we have multiple documents. Most of the times the documents are on the same topic. For example, we have the news article about the same event from different press, and we want to generate a summary for all the news articles. Then that's the settings of the multi-document summarization. And in terms of the output side, we also could categorize summarization methods into extractive and abstractive summarizations. So extractive summarizations are where we can directly take sentences that are important from the original document, and we can format a summary with those extracted sentences. So in this way, we're only using the sentences and words from the original documents, and we're not generating anything new. Another way is the abstractive summarization, where we, similar to how humans write a summary, we read the article, understand the content, and we write a summary from scratch. And definitely we can combine both together to build a hybrid summaries. So that's also another options. And also, I also mentioned query-focused summaries. So that's something that's very different from the generic summaries. So generic summaries are those summaries we try to summarize the whole documents or multiple documents. But the query-focused summarization is where we have a user's query or a keyword, and we try to generate a summary that's focusing on the keyword or the query. It's very similar to a complex question answering settings where we try to answer a query by finding the relevant passages from the documents and use those to generate a summary as the answer. And here I'm showing an example of a news from the CNN Daily Mail website. And the top part is a news article. And on the bottom, I give the reference summary, which is the summary written by the editor of the CNN. And the second is an extractive summary, which is the summary that directly taking sentences from the original document. And the third is the abstractive summary, which is the summary generated by a language model. So probably the audience can take 2 minutes to think about which summary is better, or like you can also think about why do you think some summary is better than others? What is the evaluation criteria you use to determine a good summary? Actually, think about the problem. It's very hard to have a good evaluation of the quality of a summary. And definitely different person will have a different standard and their own preference. From the linguistic perspective, we have several dimensions. We can measure whether a summary is good or not. So we can think about the coherence of the summary, the consistency, the fluency, the relevance, the informativeness, the consciousness, coverage, and also the faithfulness. These are the dimensions we can use to determine the quality of a summaries. But still, there's no very universal standard, and it's also very hard to quantify the quality of a summary, even with those dimensions. So definitely, summary quality evaluation is a very challenging problem, even for human beings. And in natural language processing, we mostly use the RUGE-M metric, which is a similarity measurement metric to determine the quality. So the idea is if we want to train an AI model to generate a summary, then we just train a model to generate summary that are more similar to human written summaries. So for a document, we can ask professional editors to write a summary. Then we can simply train the models to generate summary that are very similar to the human written summaries. And RUGE is the metrics we use to measure the similarity between a human written summary and the AI generated summaries. So here is the technical definition of the RUGE score. So it's a similarity matrix based on the n-grams. And for simplicity, I'm just showing the sense of RUGE by this example. So say if I have a query, then we have the output of the models, and we have 3 human annotators, each also answer the questions. Then we can calculate the RUGE by calculating the similarity between the AI generated summaries versus the human written summaries. So we can just count how many common words or like word overlaps between the summaries, and we can formulate that into a F1 score format, and we can get the RUGE score of 0.43. So it's just a measurement of how similar the summaries is to human written summaries. And that's already the best way we can quantify a summary, and the only way we can train AI models to write summaries for documents. And definitely summarization models also rely on data sets. So here is a breakdown of the publicly available data sets for summaries. You can see the data sets span a variety of topics. So most of the data sets are from the news domain, but there's other domains such as social media, dialogue, email, scientific papers, even bail patent. Definitely, we are seeing wider applications of summarization in more domains. So we will have more and more data to train the models and build better summarization models. And next, I'll briefly introduce the research of AI-powered summarization. So generally speaking, AI-powered summarization is not a new problem. It has been started early in the 90s, in the last century. And, by that time, most of the models are using the statistical models. And so that's the first phase of AI-powered summarization research, which are focusing on as methods. Later in the 2010, we have the neural networks, and then we start to use deep learning and use those models to build deep learning supervised summarization models. That's the second phase of the summarization research. And in 2018, we have the first pre-trained language model, which is BERT by the Google company. And that also shapes the paradigms for summarization research. And from there, people are using the pre-trained LLMs to fine-tuning for summarization. That's the third phase of summarization research. And in 2022, we have the ChatGPT, and That's also make a great like a total change to the summarization research landscape. And ever since there, everybody is just doing research on LLMs, and where our LP researchers are also exploring summarization with zero-shot and few-shot settings. And here's a very good survey of summarization research. So if you are interested in the topics, feel free to check the reference. I know it's a really good survey because I wrote it, so it's really good. And here's a breakdown of the most popular summarization methods, also from the survey. So you can see, so prior to LMs, researchers has explored different categories of methods to do summarization. From the statistical error, where we are exploring using heuristic optimization, graph-based methods. And in deep learning error, we just use different formats of neural networks, such as convolutional, recurrent neural network, reinforcement learning. Just use those different neural networks to do the job. And in the pre-trained language error, we're just using different pre-trained language models, such as BERT and BART, to do the job. I just briefly talk about some representative work in summarization. So there's a whole group of work by the graph-based summarization. The idea is the sentence that are important should be similar to most of the other sentences. So in that way, if we treat each sentence as a node and we build a graph for a document, then the sentence or the node that connects to most of the other sentences or nodes should be the most important one. So this is actually the PageRank algorithm. That's the founder of Google Page, actually, Larry Page, used this algorithm to build the Google search engine. So it's similar, right? So the web page that connects to most of the other web pages are the most important web pages and should be in the first of in the Google search. Similarly, for the sentence, we can simply find the most important sentences from a document by calculating which sentence is more similar to the other sentences. And in the neural network error, we're just using different formats of neural networks. So we have explored using convolutional neural networks or recurrent neural networks. Basically, the idea is we feed the sentence to neural net models, and the models will give a label, 0 or 1. 0 means the sentence is not important, and we should not use that in the summary. And 1 means this sentence is very important. We should include that in the summary. So we are transforming the summarization into a binary classification problem. We just give a 0 or 1 label to each sentence of the document. Then we can get the summary from a document. Nothing has changed since we have the large language models. So we can revisit the development of large language models from the OpenAI company. So in 2018, we have the first generation of LLMs, which is GPT. It's not very impactful by that time because it doesn't have a really good or impressive performance. The model has a decoder transformer architecture with 12 layers, and it's trained on a full corpus. Since it's by that time, it's not actually very impressive. Until later in 2019, the OpenAI company released the second version of GPT. The model is no difference in terms of the technical, but they only use larger models and use more data. So you can see the parameters of the model increase from 117 million parameters to 1.5 billion parameters. And the researchers have found that the models, without any change of the architecture, only by building larger models with more data, it has much more capabilities compared to smaller models. And researchers have found the models have some emergent zero-shot learning capabilities. By emergent zero-shot learning, I mean the models doesn't need any fine-tuning. So you take the off-the-shelf GPT-2, it can already solve some problems. For example, you can give a question and you leave the prompts here, answer, then the model will complete the sentence and give you an answer. It can also give you the like whether the cat or the hat has a higher probability. So this is the first time people realize that we don't actually need to fine-tune the models. We can directly take the off-the-shelf LLMs and use them for different purposes. And that also applies to summarization. So researchers have found like they can use simple prompts like they give a document and they just write this TLDR, and GPT-2 can complete the sentence and give you the summary of the document. And by that time, you can see without training the zero-shot, LLMs can already get a relative good performance in terms of summarization. Although it's not comparable to the supervised training models, the zero-shot capability does show a great potentials. And the things changed totally after we have GPT-3 in 2020. GPT-3 is even much larger, so it shifts from 1.5 billion to 175 billion parameters. Also, the training data shifts from 40 gigabytes to over 600 gigabytes. Then the GPT-3 is a totally different story, and people realize that the LMs and the few shot and zero shot capabilities is the future. So that's where people start to work on LMs, especially for summarization domains. So then we have the new paradigm for AI-powered summarization. So traditionally, we'll just take some models and we train the models on the domain-specific data using the gradient descent. And after the training on this, we have a model that has good summary capabilities. But after GPT-3, we realized that we can directly use the few shot or zero shot promptings. So we don't need to actually train the models. The model is good to generate summaries for different types of documents itself. And here is just the comparison of the architecture. So the bidirectional encoder, also the encoder-decoder architecture has been used by other companies for quite a few years, but OpenAI picked this decoder-only architecture, and I don't think they have any actually good reason to pick this architecture. I think to me, they just happen to use this and scale it up, and it happens to work. And so everybody just follow OpenAI to use decoder only. So naturally, there shouldn't be too much difference between different architectures. And after GPT-3, we can see the LM generated summaries already has a on par with human written summaries. So here's some comparison between summaries by different models. You can see GPT-3 models summaries are already preferred by human beings compared to other summarization models. And also in terms of the root scores, the models also gain pretty solid root scores. And so that's how summarization shifts in the large language model era. And next, I'll briefly talk about one of my papers. So it's an iterative framework for self-refinement summarization where large language models. So one problem of machine-generated summaries is they contain some factual or faithfulness errors. So researchers found like almost 30% of the summary generated by the models are not faithful, or they contain some factual errors. And but on the other hand, a good summary should not make errors. It should be factual and faithful to the source document. So in this work, we propose a new framework for summarization, LLM-based summarization, where we ask the model to revise its summaries itself. So the framework is pretty simple. So we start with given document to the models, and the model can generate a summary, which is the initial summary. Next, we pass the summary and the document to the models and ask the model to give some feedback on whether the summary is good or not, and give some suggestions whether the model should refine the summary or not. And we then pass the feedback to the models, and the model will start to refine the summaries based on the feedback it gets. And the model can repeat these two steps until it finds there's no need to refine the summaries further, and it can give us a good summaries already. And for this summit, which stands for Summarization Iteratively, we propose this architecture where we have the evaluator that's gonna generate feedbacks for a summary and a document. And we also have the summarizer, which can give the initial summary and can also refine a summary based on the feedback. And we also have two components, the knowledge extractor and the topic extractor, to augment the whole refinement process. And altogether, we build this system where we give a source document, and the evaluator and the summarizer will go multiple iterations to generate feedbacks and refine the summary, until we have a good summary as the output. And empirically found that if we just ask the evaluator to give random suggestions, the performance is not good. So we limit the possible refinement operations into this format. So the evaluator can only suggest we add a sentence, add information, or remove some information, or rephrase some sentences, or simplify some sentences, or keep some sentences unchanged. So it can only suggest any operations from the list. And also we design a few stopping criteria to ensure that the iteration doesn't keep going forever. So if the evaluator finds there's no further refinement is required, then we'll stop the process. We also have several rule-based stopping criteria, such as if we reach a maximum iteration numbers, we'll stop the criteria. Then from the automatic evaluation, we can see there's a consistent improvement in terms of the quality of summary from our iterative summarization framework compared to prompting to LLM itself directly. And we also found that the faithfulness of the summaries also improve after we have the iteration process. So definitely the models can recognize its own error and correct its errors. We also conduct some human evaluations where we give the summaries generated by our systems and also other LLMs, and we ask human annotators to pick their favorite summaries. And from the human annotation results, our system also has a much higher preference by human beings, and also humans prefer the summaries to other models. We also conduct further human analysis to study whether does the refinement of the model actually follow the generated feedbacks. So we take the summary before and after the refinement and ask humans to justify whether the refinement is following the feedback it's given. And the results shows yes, over 90% of the edits performed by the summarizer actually is following the instruction given by the evaluator. Also, we also conduct another human study to study whether the refinement actually improved the quality of the summaries besides the numbers I showed earlier. So we give the summary before in each iteration to human annotators and ask humans to determine which summary is the best. So surprisingly, we found that up to 2 iterations, the summary quality improves, but after 2 more iterations, the quality of the summaries are not noticeable to human beings. But still, our models will ask the model to perform this refinement. So that actually leads to the problem of overcorrection, where LLMs itself has a different standard and criteria to refine the summary, which is not alignment with which is not in alignment with human judgments. And definitely for that, we need to involve human being in the loop. So human in the loop summarization is definitely one of the most popular topics right now. Now here's a case study. So given summary from the first iterations, the evaluator gave two suggestions where it should remove the orange sentence and rephrase the blue sentence. And the summarizer can directly follow instructions to refine the summaries. So some simple takeaways. So LLMs are powerful agents to build integral application systems. So this work is one of the prototypes for building the multi-agent systems for LLMs. And the human in the loop is very important for model behavior alignment. And also, if you use ChatGPT to summarize a document for you, probably can also ask the model to refine its answer. And according to our experiments, the quality of the summary will improve up to 2 iterations. So next, I'll briefly talk about the future directions in summarization research. So a lot of researchers have asked, even myself, like since we already have the powerful LLMs, do we still need to do research in summarization? Does ChatGPT give you good enough summaries? But still, there are still a lot of open challenges for summarizations. First challenge is the hallucination. So the model still hallucinate and make false statements. How can we correct those hallucinations in the summaries? And the RAG, retrieval augmented generation, is one options to mitigate the hallucination, and also our model, which is a type of self-reflection, is another possible direction. How can we resolve the bias issue in the generated summaries? So there is a lot of research on bias detection and migration right now. And as I mentioned, LLMs are too big. They're like we can't hold them in small GPUs or locally in laptops. So how can we improve the computational efficiency of summarization models? There are a lot of directions, such as the hardware acceleration, model pruning, quantization, parameter efficient fine-tuning, and also distillation. So that's also hot topics in LP research right now. And another open challenge is the personalization problem. So as I mentioned earlier, different person has a different preference for summaries. Then how can you build a model that are following your own standards and can generate a personalized summaries for you? So for example, if I read the NBA sports news, I like LeBron James and the Lakers team. So I will hope the models can summarize more information about the Lakers team. Now, how can I make sure the models can be personalized to myself to following my own preference? That's also another open challenge. Also, the interpretability and explainability of the LLMs. So we know the LLM can generate a summary, but why does the model generate this summary? How can we interpret this process? That's also a remaining problem. And there are a few future directions for summarization research. First is summarization beyond text. So definitely we have more data formats to summarize. So if I give a video to the models, can the model generate a good summaries? If I give an audio or I give an Excel data, then can model summarize data for me? So it's also promising direction to building the multi-model summarization models, which can integrate different modality of data. And there's more emerging summarization tasks, and that's are more related to real-world applications. So how can I build personalized summarization models or real-time summarization models? or the sentiment-aware summarization models. So those emerging tasks are very important, especially for the applications in critical domains such as legal, clinical, or medical. The third direction will be the ethical and responsible AI practices. So how can we grounding the models in social and cognitive science for accuracy? And how can we build domain-specific summarization models? So say if I have a few documents in the medical domain, then probably ChatGPT won't do a good job because ChatGPT is not familiar with the domain knowledge, or it is not familiar with the terminologies. Then how can we take the off-the-shelf models and build a domain-specific models that can build for the domain-specific applications is another research directions. And as I said, there's we can explore multimodal inputs. We can ensure the generated summaries are trustworthy. Make sure the summaries are fair. There's no bias, and it's also interpretable. And we also can explore the data sources we use. So we can augment the summarization with the external knowledge to improve the generation accuracy and mitigate the hallucination problems. And definitely besides that, RP could also be applied to more domains, not only in the summarization research. So RP could be integrated into the bioinformatics, social networks, software engineering, medical domains, geology, education, and so on. So I know the audience probably are from a diverse background, and definitely there's a lot of possibilities to apply LM to your own discipline and to accelerate the discoveries or automate the workflows or improve the efficiencies or make new findings. So there's a lot of possibilities for applying LP to the science domain. And definitely for LP researchers, our ultimate goal is building the intelligent personal AI assistant, so similar to the Jarvis in the Iron Man movies, if you are familiar with. So that's pretty much of my talk today. So here's a participant survey. So you can click, you can just go to the URL link, or you can scan the QR code to take the participant survey. And I can also use some time to take any questions.
Explain a little bit more about multimodal models. So if I'm using ChatGPT and I'm give it an image and ask it about describe the image, and I'm kind of fascinated by that, how it works. Is it a language model using another separate model, or is it all included? Is the image being tokenized?
Yeah, exactly. It's the magic of tokenization. So as I said earlier, language models can only take numerical vectors. So for it to process a text, like it needs to tokenize the plain text into the vectors. And we can just do the same for images. We can use the tokenizer, which is definitely another tokenizer that can tokenize images into vectors. And the model will just like process the tokenizer, do all the calculations itself. And that's actually a very broad research topics, and a lot of people are doing that. And like one of the most popular visual tokenizer is called Vision Transformer. If you like search reality, then it's basically that's the first try to just take an image. Like each pixel will be one of the token, and it can serialize the image into a long sequence of tokens, and then use the tokenizer to encode the image into a numerical vector. Then the model will be able to process those. Yes, please.
I've heard that the summarization can be less good when the content is like more technical. Is that true?
Yeah, that's actually a tricky part because it also depends on how you define the technical or how you define good, right? But generally speaking, most of the models are trained on plain data, plain text, which are such as the websites or news on those data. Then definitely the models works better in those domains. But for a more specific domain, if you have more formulas or equations in the paper, then likely the model will be less like effective to summarize those papers. So that's definitely true.
I guess I'm thinking like sometimes when technical papers are written, there might actually not be very much superfluous language. It's like the model know if actually it's reached saturation or like I can't distill this further, you know?
Yeah, that will happen, especially if the domain will be very different, and if the model hasn't seen the relevant information during the training process, and likely it will be not that good in summarizing those. So that's why I said earlier there's another direction in building the domain-specific summarization models. Like for if you have a specific domain, how can we gather some data for that domain, and we can build a better model for the specific purpose.
There's a question in the chat. What model of AI tool would you suggest for application in medical research?
Yeah, for medical, so there's a lot of works in building foundation models for medical domains. They just gather the data from the medical domains and use those to train their specific models. So I know there's a popular model called Bellman GPT, which is new models proposed by some researchers from Lehigh University. Probably you can use that as a reference to see relevant models. So that model is trained on the biomedical domains specifically, so it can handle the data better than general purpose AI tools.
Thank you again for your time. Thank you for the workshop.